Hey everybody, how's it going? Okay, not too shabby? Everybody fine? We're almost to week 5, and that's the scary thing, right? So just to put you in mind of what's coming up, I got the schedule up here. Today we are going to have, of course, your assignment is due, right? Beyond that, just thinking about what's coming up. A week from Friday. Yeah, sorry, what was that? Oh, God, yeah, sorry. Assignment 3, right? I forgot. Assignment 3 got released late, didn't it? Thank you. Okay. So, thank you. Got released late, so it's Saturday. Good. See, I'm just following the schedule. But the schedule got broken. All right, so assignment 3 is due Saturday. Assignment 4 should nonetheless post today, and I want us to return to the regular schedule. I don't want to shift us over regularly. Because in particular, assignment 4 should be due a week from today so that you've turned it in and done it before the exam that is happening a week from Friday. Okay? So, exam review. This is a week from today is my cushion day / exam review. I think what I'm going to do is I'm going to take it as the exam review, and I might release a little bit of recorded stuff between Monday and Wednesday to finish off the missing time, right? Because I painted myself into a corner. I'm a day late right now on the lectures. I think it's probably better for you, maybe, to have the review be live, because then you could interact. You could ask me questions that you're unclear on, right? And we can go over stuff. I may kind of 50-50 it. I may do something like that, but I think I want to keep at least part of the review live, okay? Yeah. Yeah, so there's a practice exam that we've released in the past that we will release again with small modifications. Yes. That is an excellent question. I guess I should talk with my TAs. Generally speaking, we definitely get it out over this coming weekend so that you've got it for the week, and then we generally post the answers like the day before the exam. Yeah. Maybe I didn't. Sorry, we have a faculty interview candidate today, and that's screwed my schedule over. I thought I did, but I probably didn't, so let's do that real fast. What if I pushed it to my COGS 108 instead of this? That would be awesome. Today's 11? No. Yeah, that seems right. Okay, done. Thank you for that. What else? Yeah.
So the exam is in person?
Yes, the exam will be in person here. It'll be a 50-minute exam. It will be largely based on things you have seen in assignments. It's not going to be like a new kind of question, okay? There will be, there is still some doubt about the media. I kind of would like eventually to move us over to being actually in notebooks live, but there's concerns about Wi-Fi and trying to do it that way. I think it's probably safer to just stick with the dumb paper exam, as terrible as that is. Yeah. So yes, what I have done in the past and what I intend to do this time, and I will release all of this when we talk about exams more later, is you are allowed a single sheet of paper cheat sheet. In my opinion, the use of a cheat sheet is in the construction of the cheat sheet. The very act of making it is what cheat sheets actually help, right? You're generally under so much time pressure that even having a cheat sheet, if you don't already know what's on it, is not very helpful. And for that reason, I highly encourage people to make handwritten cheat sheets, because for most people, that helps learning compared to just copy-pasting stuff. Right? You've probably heard all that before, but I'll say it to you. Yeah, so generally speaking, that's the format. 50 minutes, a lot more multiple choice than anything else. There will be some longer problems that involve working out some math. When it's on paper, I never ask real programming questions. Like, I don't make you handwrite scikit-learn stuff. If I ask a programming question, it's going to be multiple choice. Okay? Just so you know. Any other questions for right now? There will be more exam detail next week. Okay? It will also be posted online. Like, I will put out a big bullet point list of stuff to do and not to do. Okay? And there will be the review exam stuff, the test, practice test. Okay, if that's all good, let's talk about metrics. I forgot to even check. We got all the way through logistic regression, right? Yeah, we did. Yeah, this is all just review stuff. Okay, great. So metrics, what do we got? You are now ready to do machine learning, okay? What have you seen so far in this class? You have gone through the whole review process and getting everybody up to speed, talked a lot about the math, like, monotonic functions and convexity and that stuff, all the background. Then we went into regression so that we could talk about how to predict continuous outputs, right? And we added into that regression conversation things that are hyperparameters, like the term lambda for weight squishing, for regularization. And we talked about multiple different loss functions for regularization, the standard ordinary least squares, which is an L2 norm squared on the residuals vector. And we also talked about a different kind of loss function for regression using L1 norm on the residuals as quote-unquote robust regression. So we have two different kinds of regression, right? And now this last week we talked about classification. And now we've talked about decision stumps and trees. We've talked about k-nearest neighbors. We've talked about logistic regression, 3 different algorithms, each of which have their own sets of hyperparameters. So for instance, right, k-nearest neighbors, the k, that's a hyperparameter. You can choose 7, 13, 23. How many neighbors? And the number of neighbors you pick is going to give you different answers. Logistic regression, I didn't say this in the logistic regression bit, but it's one of these linear algebra algorithms. The log loss that we were talking about, you can regularize that. you can put log loss plus lambda L2 norm of the weights, just like we did for regression. Logistic regression can be regularized in exactly the same way. Put a lambda on the back side of it, add another term of weight squishing. Okay? So everything has its hyperparameters. You have not just hyperparameters for one algorithm, you have multiple algorithms in both regression and classification to choose from. So here you are faced with a choice. You have a machine learning problem to solve. You have, whether it's a regression problem or a classification problem, you have multiple tools in your toolkit. How do you pick? So that's what we're talking about this week, right? That's exactly what we want to get to. We're now at the place where you can actually do the machine learning thing from front to back. You can get your data. Somebody was saying, oh, this class is easy without COGS 108. You're going to have to deal with your data. If somebody gives you nice data, you're all ready, but maybe you have to, deal with the data by filling in missing values or, understanding the distributions of the data so that you know what kind of an algorithm might be appropriate or might not. If you can't draw a line to separate out penguin species, don't use a linear kind of algorithm. Use something like a decision tree, right? Exploring the data, step 1. Step 2, identify, because of your explorations, all the potential solutions that might make sense. Step 3, try those different solutions, try different algorithms, try different k values for k nearest neighbor or any other hyperparameter for every possible algorithm. And how do we do that? Well, we've already talked about this, right? In the broadest sense, we take all of our data, we chunk it up, we use some for training, some for validation, some for testing, right? And the whole point of this process is that for decision trees, right, we take one kind of tree, we train it on the data, we take a different kind of tree with a different set of hyperparameters, train it on the same training data, do that for all 35 trees that we imagine we're going to try. We do that again for k nearest neighbors. We do that again, and we have whatever. At the end of this thing, we have 100 machine learning setups trained on the same training data. Now we've got to evaluate them on the validation data. These trained 100 algorithms and hyperparameters, we run these trained things through the validation data, and we pick the best one, and we say, this is my algorithm and hyperparameters. I'm going to use it. There's a problem there. Pick the best one. It is not always clear what that is, right? Because measuring best means we've got a yardstick, we've got a metric, okay? And there is always more than one metric that is applicable to a problem. So you might find a situation where algorithm 36 is best when you use this metric as your criteria. And if you choose a different metric, which is maybe equally reasonable, it's algorithm 12. Okay? So what does it mean? We have to care about what our yardsticks are, right? Like I said, it's not always clear why we use one metric and not a different one. So let's talk about metrics, because they are the key before we can really get to the full model selection task. All right. So that's where we're at. So how do we measure what's good? A very, very natural thing is to use the loss function itself, right? So if I'm fitting two different regularized linear regressions, What's my total loss? OLS plus the regularized term, right? So that's great, because the very idea of a loss function is that we have defined it such that we assume that making the loss function better is going to make us better at the task. Why is a loss function not always enough? Anybody got some examples? Other than just reading off my bullet points. If we're doing model comparison, like, k-nearest neighbors versus logistic regression, can we compare k-nearest neighbors loss to logistic regression's loss? No, because they're different equations, right? So bare minimum, when you're doing algorithm comparison, you can't use a loss function because the loss functions are different for different algorithms, right? Okay. Even if you're just using different hyperparameters for the same algorithm, you might be interested in looking at the problem from different viewpoints. So the loss function has got a particular viewpoint on what is good performance. Maybe you want to check a slightly different viewpoint for looking at performance with respect to false positive rate, right? So false positive rate, if your algorithm is logistic regression, that's minimizing the difference between the probability of correct and the actual probability predicted, right? But that includes false positives and false negatives both, okay? But if we really just care about false positives for whatever reason, then maybe we want to look at false positive rate specifically, and that could be a metric that we care about. So we're going to talk about these in details, but using different viewpoints is why we may be using different metrics even than just the loss function. So the list here you can find on the scikit-learn docs, by the way. As always, you should be spending time with the scikit docs because you can learn a lot from them. Just going, I don't even know what F1 score is, and what's the difference, especially between F1 micro and F1 macro, I suggest you click on those because the docs actually are going to tell you things that I don't have time to, right? What you'll see immediately in the scikit docs is that metrics really do have very particular uses. So there are metrics that are specific for classification that don't work well for regression, and vice versa, right? So you can see they're broadly categorized into classification, clustering, and regression. Okay. So beyond the metric, which we're going to talk about further, we also have to talk about the idea of benchmarks. So benchmarks are data sets and problems that we consider to be exemplary of this kind of machine learning task. So visual classification. Give a machine learning thing a JPEG, and it's supposed to tell you this is a cat or this is a car. So there are common benchmarks that we use to talk about visual classification tasks, right? And we use these metrics that we're going to discuss to measure performance at these benchmarks. So being able to actually compare different kinds of algorithms on these benchmarks using common metrics, right, is what gives us the ability to say, hey, high score, baby. This is the current best at one particular kind of visual categorization, this algorithm right here. And again, it's very important to keep in mind the difference between the loss function, which is the objective we're minimizing to make the ML system, and a metric that might have nothing to do with that loss function, but still measures an aspect of task performance. Right? So, yeah.
So typically our benchmark is like
You got it. So here is an example of a benchmark. So ImageNet is a set of, I don't even know, like millions of smallish images, right? And each one of them is labeled, oh, it's a cat, or it's a bike, or whatever, right? So ImageNet is this classic benchmark. And what you're seeing here, by the way, this is, oh, I thought I had the link here, but this is a website called paperswithcode.com. Papers with Code. It is one, I would call it probably the preeminent current scoreboard in machine learning. It hosts loads of benchmarks like ImageNet. It has linked up to it papers that have their associated code freely available, usually on GitHub, right? So you can actually see the implementation of these algorithms. So if I click on this, you'll get Fix Efficient Net, whatever that is, right? Whatever that paper is. You'll see both what people wrote about, and you can look at the code that implements Fix Efficient Net. So Papers with Code is like one of these places that has helped stimulate an enormous growth in machine learning because there is this scoreboard and people are trying to best it, right? Small caveat. How much better do you think this little current best performing dot is than this dot or this dot or this dot? Is there a statistically significant difference in performance here, or is this just a high score? That's one of my concerns with this approach that we have really in machine learning, this high score approach, okay? If we were taking these algorithms and using them not on ImageNet, but a different benchmark that is similar in nature, would the high score here still be the high score? The answer is largely no, right? Just be aware of high score on a video game doesn't mean you're the world's best video game player, okay? So, but nonetheless, we still can see over time a strong increase in performance on this metric, which happens to be top 1 accuracy, right? For those of you that aren't familiar, the idea of classification is that we make a prediction. And what we've always been talking about has been top 1. But some kinds of neural networks, what they do is they predict not one class, but they'll say, here's 200 classes. And I believe that the most likely one is this one class. But if you let me guess my top 5, here's my list of top 5 guesses, right? So you don't have to use top 1. You can use top 5 as a generalization or a top 10, right? But you can definitely, on Papers with Code, click this little pull down and see what the top 5 scoreboard is instead. Okay? So I really recommend that you go off and explore this on your own. So just like, again, what is ImageNet? It's 14 million annotated images, right? There's a particular, not just the images, but it is got a particular, oh God, I'm blanking on what the right word is right now. It's not schema. What's the word for when you have a structured set of how words get used to describe something? Ontology. Jesus. So there's a structured ontology of how the labels are created, okay? So ImageNet is beyond just the images. It's also the words used to describe the images is a fixed kind of ontology. So yeah, it's a pretty impressive data set and one of the standards for doing visual classification. So you can explore benchmarks. You can explore algorithms using paperswithcode.com. All right. So that's where we're at. We need to do this in general with our machine learning systems. Now, let's be really clear. Performance on a benchmark does not equate, if you have a different visual classification task, to performance on that different task, right? But the idea is that benchmark performance is maybe helpful in guiding your selection for what algorithms to try on your particular visual classification task, right? Okay, stepping back from the benchmarks, just in general, imagining you're not working on a benchmark, but just a particular data problem. We got a training set. It's got +1, -1. We've got a function that classifies things into being positive class or negative class, right? So we're going to learn a set of parameters W that create this forward step, this classification. Given the X's, get out a Y label for this person is sick or this person is healthy from their data. So in general, we're going to talk about the idea of the training set error. And in this case, right, what is this one called? Anybody remember what this error, this metric is called? I've shown you this math before. What does it do? Maybe start there. Yeah?
It's like the percentage of incorrect classifications.
Exactly. It is the percentage of incorrect classifications, or also called the hard loss or the misclassification error, right? What it does is it's a 1 if for a particular input x of I, if our prediction of x of I doesn't match the true label y sub I, right? Add up the ones, divide by the number of data points in the training set, and what you get is a ratio, not a percentage, to be really proper about it. It's a number between 0 and 1. 1 means we made all errors and no corrects. 0 means we made all correct and no errors. Okay? So this is the hard loss or the misclassification error. So if in training we made 3 errors out of 10 training data points, that would be a loss of 0.3, or a metric, a misclassification error rate of 0.3. Okay, separately, we can measure on the testing set, right, the same metric. This point, it's up over Q data points in the test set, exact same thing, and we could have a different metric, right? I think everybody's got this by now. So, obviously, we don't just want to use misclassification error for a variety of reasons. So the misclassification rate is one viewpoint on classification. So if we just sum up the number of, so we often have a case where maybe one class is much more common than the other class in the data. So with my sick people example, what if we have cancer patients, right? Cancer patients are relatively rare. They're like a percentage, like maybe 1%, maybe less of the entire population. So if you have a data set of people in a medical environment, the data set is going to be mostly healthy people, that is negative class. And very, very few positive class individuals, cancer patients, right? This is called unbalanced data. It's very, very common in real-world problems. And oftentimes, even though you have relatively few cancer patients, you care dramatically about getting the diagnosis of a cancer patient right. They are probably more important to you to take a cancer patient and have your test accurately say this person is cancerous than it is for you to accidentally do the other thing and take a healthy person and tell them they have cancer. Take a healthy person, tell them they have cancer. Obviously, they freak out, but they don't die because when the doctor examines them further, they figure out they're healthy, right? But if your medical test misses a single cancer patient, and that cancer patient, sorry, I shouldn't say cancer patient, I should say cancerous individual, because they're not a patient yet until we know they have cancer, right? If you're trying to detect cancer and you miss a single example of cancer, that person doesn't get treated, probably they die, right? So it's very important to us to make sure that when we have this situation, that we don't end up just caring about classification error. Because if we were using classification error to design our algorithm, what is going to be good performance? I will just always predict healthy. If I always say healthy, no matter what the data is, I'm only wrong 1% of the time, right? Or actually, in this case, it's one-tenth of 1% of the time, right? So if I'm only wrong 0.1% of the time, I never have to actually use the data. I can just say everybody's healthy, right? And I'm doing really good by misclassification error. So by the way, things like COVID, even at the 2020 peak in August, they were also similarly like this 0.1% of the population in San Diego at that very moment, right? COVID diagnosis, just like cancer diagnosis, is this case where it's relatively rare to be positive. So that affects how we design our systems. Does anybody have any questions? Is this making sense? Am I going too slow and this is just really obvious? Okay. Great. So again, somebody comes in, you're looking at ImageNet or whatever equivalent thing on a scoreboard, on a benchmark, right? And you see somebody makes a claim, our classifier was 94% accurate. What I want you to think is, what does that imply exactly? 94% accurate, is that misclassification rate? Would I care about misclassification rate in this particular instance? Because, like for instance, if you look at the data set, and the data set says 72% of it was benign, 16% non-cancerous, 12% malignant. So if it just guessed the most common class, what would be my accuracy rate? That data-free approach I was talking about. Just pick the most common one and say everything is benign without looking at the data. What's my accuracy rate going to be? 70%. Exactly. Okay, so now 94% doesn't look so hot, right? It's only 20% better than quote-unquote chance or blind choice, right? So 94% seemed like a big number when you were thinking implicitly 50% or maybe 33% if you were imagining a balanced thing of 3 classes as chance level. But when you look at it, chance level is 72%, right? So what if it turns out that if we use the viewpoint of false positives and false negatives, what if there's a systematic concern, right? Like malignant cancers are the real bad deal. They're the ones that you've definitely got to catch. And if we misclassified a substantial number of truly malignant cancers, because again, malignant is rare, so getting a lot of malignants wrong doesn't really affect the misclassification rate much, right? That's potentially a problem. Okay. So this is my fun slide, just to remind everybody. If you have binary classification, just 2 classes, we talk about the idea of, okay, we're going to look at a contingency table or a confusion matrix, 2 words for the same thing, right? If there's truly positive class and our test accurately predicts them as positive class, that is a true positive. Your pregnancy test worked right, you are actually pregnant. Okay? If you have a truly negative class data sample and your class properly predicted it as negative class, congratulations, you're not pregnant. That's the truth. Okay? But we can have two kinds of errors. We can have the so-called type 1 or false positive error, where you tell somebody who is not pregnant that they are. And you can have the so-called type 2 error if you're a statistician, but let's just throw those type numbers away because they frickin' suck, and just say it's a false negative because that's descriptive. This person is pregnant, but we falsely told them they're not. Okay? So just keep that in mind. This is the basis of everything we're going to talk about in classification land. False positives and false negatives. True positives and true negatives. When you see a confusion matrix, big numbers on the diagonal are good. Big numbers on the off diagonal are bad. Okay? So yeah, we want to have our true positive rate be high. What is a true positive rate? Okay, the probability that given that the actual data sample is positive class, given a true positive label, we want the probability that we will predict it to be positive to be high. What that means is, hey, we've got this confusion matrix here. This is where the true positives are. How many true positives do we have in this cell? Take that number, divide it by the total number of things in this entire row. Divide it by all the true labeled things. Okay? That is what the true positive rate is. This number divided by the sum of the entire row. Now, I like to use the word true positive rate. You will find other people who will use the word sensitivity to describe the same thing. Or even worse, you will find a third set of people that will call this recall. I apologize. This is because several different fields all use the same statistics, and yet each field chooses a different piece of jargon. Okay? How can you remember this? True positive rate, I hope, is self-evident what it is. Sensitivity, you can think of this as I am sensitive in my test to the existence of positive class. If it's a positive class instance, I'm going to accurately label it in a sensitive way. I'm not going to miss any positive classes, right? I'm sensitive to their existence. You can also think of recall the same way. I'm going to accurately recall whether something is positive class, okay? So true negative rate is the probability that given that something is actually negative class, I have predicted it to be at negative class. Just like before, that true negative rate is over here. Take the number of things in this cell of the confusion matrix, that's the numerator, and divide it by the sum of everything in this row, in the negative row. Okay? Again, jargon, other than true negative rate, some people will call this specificity. How can you remember that? This test is specific to only the positive class. I will not accidentally grab negative class instances. Okay? I'm specific only to the positive class. Okay. So we want those to be big, right? We want the off-diagonal stuff, which is the false positives over here. Sorry, the false positives are over here. I'm not saying stuff right. And the false negatives over here, right? So we want them to be small. Okay. So, see this link? You're going to become really familiar with this wiki page. So precision and recall is got this giant table on it. Let's understand the nature of it. At its core, this table is the confusion matrix. Here are the actual positives and the actual negatives. Here are the predicted positives and the predicted negatives. And this central core is the confusion matrix. Here are our true positives. Here are our true negatives. Here's our false negatives and our false positives, just like we've been doing. Okay? So this is actually a table beyond just the contingency table. It's about a bunch of metrics that are built from this core. All right? Everything else that's not in this core, these are metrics that are built from true positives, true negatives, false positives, and false negatives. Okay? And the way you should understand it is the following. Remember how I said that the true positive rate, i.e. recall, aka sensitivity, right? It's built from taking this cell and dividing up by the total number of positives. Well, here it is, right? It's put in this matrix because it involves this row, right? It's calculated off of this row of the confusion matrix. Likewise, positive predictive value is the number of true positives divided by the total number of positives. It's based off of this column. Okay? So anything that's in color is built very directly from this central confusion matrix. If it's in white, like the Matthews correlation coefficient, or where's F1 score, right? These are composite scores. They're built out of combinations of true positives, true negatives, false negatives, or similar things that are built off of those. Okay? This is like that attempt, I don't know, like anybody into cameras or cars or one of those other things that have a lot of what I call measure baiters, like where people really get interested in a spec, like how many gigahertz your CPU is or how much RAM you got. And it turns out that one spec doesn't actually tell you everything there is to do, right? Like you can have a really nice camera that's got a low number of megapixels or stuff like that. Okay. So these white scores are these composite scores where people tend to use these to compare stuff. But the thing is it's a composite. It's kind of like just kind of have like a grade of A, which includes, some people are better at one thing and some people are better at others. So the composite hides information. But it is, if you just want to look at one number, maybe this is your deal. Okay, let's talk about a few of these. Let me just see where I'm at. I'm kind of slow. All right. Just a reminder, how do these things work? So sensitivity, that is true positive rate. If you look over here at this graph, everything on this side is actually positive. This entire left side is filled with instances that are actually positive. But our algorithm has selected as positive class those things inside the circle, right? So it's missed some of the actual positives. Everything out here, this is a false negative. Okay? So sensitivity is the number of things inside the circle that are actually positive, the selected that are positive, divided by all the positive examples. Specificity is this part over here, the things that I actually selected as negative over the things that are actually negative. Okay, we can do that for precision. So precision is different. Precision is the same as, precision is different than sensitivity because precision is normalized not by the things that are truly negative. It's normalized by what my algorithms select. The things that are truly positive. My bad. It's not normalized by the things that are truly positive. It's normalized by the things I selected as positive. So it's how many of the things I said were positive, what proportion of them are actually positive. And that's a different viewpoint than looking at, of the things that are actually positive, how many of them did I select? Okay, so these are complementary: sensitivity and precision. They're complementary because they're normalized. One of them's normalized across the row, and one of them's normalized across the column. Okay? So, these are our two big tools for looking at classification: sensitivity versus specificity trade-off, and precision versus recall trade-off. You're going to need to spend some time with this. You're going to look at this 10 times before it really makes intuitive sense. Maybe more like 20, okay? Don't freak out. It's like this for everybody. But you're going to have to go back over this again and again and again until it's second nature. Okay, let's try to build some intuition. Here I have a confusion matrix, right? These are actually positive class individuals. There's 40 of them. These are the people we predicted as positive class. So, keeping in mind, sensitivity is true positive rate. Specificity is low false positive rate. What do we think is happening here? Is this high sensitivity, low specificity? High for both? Low for both? Low for sensitivity, high for specificity? Yeah? You think it's high for both. You think it's a B. Okay? So let's look at it. Sensitivity is true positives over total positives, right? So that's 30 out of 40, or 75%, right? Okay. Specificity is true negatives over total negatives. So that is 50 out of 60. So we can argue about whether 75% is high or not. I'm going to call it high. Okay? But I think it's pretty clear that 5/6 is definitely high. Right? So this is reasonably good. We only have 10 false negatives. No, 10 false negatives. See, even I get it confused. And we only have 10 false positives. All right, just note in general, there's no reason except for the fact that this is how this was constructed, this example, why these columns sum up to the same thing as these rows, right? It doesn't have to be the case. There's no reason for row sums and column sums to be equal. It's just the particular construct here. Okay. So yeah, 75%, the false positive rate. So specificity is the inverse of the false positive rate. Okay? So specificity is 50 out of 60. The false positive rate is 10 out of 60. Right? Just to be clear. But they're measuring the same damn thing. It's just that one's the inverse of the other. Okay? So false positive rate here is low. True positive rate here is pretty high. Okay, true negative rate, the specificity, like I said, is 50 out of 60. And the false negative rate is only 10 out of 40 here. So again, true positive rate, false negative rate, they're inverses of each other. You're gonna have to go through this. All right. We're going to stop there, and we will pick up again on Friday. Good luck. Hope A3 goes well. Oh, by the way, I should have said, yes, there was a mistake on the exit quiz where the log wasn't there, and yes, everybody's getting points. That's me. That's on me. I tried to do that quiz in like 11 minutes. That's how I tried to make that.